We're going to continue our discussion on algorithmic differentiation. Just to review a little bit, we discussed this simple problem with two variables, or two inputs, two outputs. And on the left side here, we broke up these calculations into simple operations. And the idea was that in a computer, right, there's no function that just says, take two arguments, multiply them together, and add them to the sign of the first, right? I mean, this is the computer has an operation to multiply two numbers, to take the sign of a number, to add two numbers. And so this is kind of how we've broken it down into this set of steps. And the idea was that each step, just usually just involves one or two numbers here. We know how to take derivatives for each of these or can program that. And via the chain rule, we can then provide derivatives for an arbitrary complex set of operations. Just like we can compute an arbitrary complex function, we should be able to compute an arbitrary complex derivative across those same set of functions. So the idea was that normally we just send in, a variable or a vector or whatever, and it operates. But instead, we're going to change each number to, instead of just containing a variable, it would contain the derivative of that variable with respect to an input of interest in this case. So this left-hand side shows the operations that are occurring on that variable, and on the right, we've been following with the derivatives. And so we worked that out last time, and it looks something like this for this example. Some things to note or to recall here. Just like, so one thing that trips people up is that we sometimes think of this like symbolic differentiation. So we get to say V5, for example, and we think, okay, I need the derivative of this expression with respect to X1 or V1, right? So then we say, well, V3, what is that? Okay, that's V1 or V2. So what does that depend on? Okay, and we plug that in. We say, what does V4 depend on? Okay, that's sine of V1. We want to plug those all in as if it was like calculus, right? We're moving them all in. And we could do that. We could move them all down and then take an expression and differentiate with respect to V1. But the problem is that is symbolic differentiation, and that's gonna lead to that sort of expression bloat that we saw before. Just like we don't do that when we're evaluating the function, right? When we're evaluating V3 plus V4, we don't go back and say, what was V3? Okay, that was a product, let's put that in, and V4 was a sign. We don't reevaluate. When we evaluated the sign of V1, we just stored a number, and that became V4, right? So now when we add V3 and V4, we don't really know or care how V4 got that number, that it was a sign. All we know is that it's a number. So at this stage, we're just adding two numbers. Similarly, when we go over here to the derivatives, we're just adding these two derivative numbers. Or like in this example with the sign, we know the derivative of the sign is the cosine of V1, and via the chain rule times the derivative of that argument. So when we get here, remember that now we're not just storing V1, but V1 dot, and the same for every variable. These are just numbers that we have at our disposal. So the complexity doesn't keep growing like symbolic differentiation. It stays, we're doing basically the same type of operations that we're doing for the function. Just basically, taking, so in this case, taking a sign or multiplying some numbers. And they're all going to be dealing with variables that we had before. Just like here, we're using variables that we computed previously. Here we're using variables that we've computed previously. So by the time we get to the end of this analysis, we have our functions of interest, and we have the derivatives of our functions of interest with respect to a single input, right? All of these here were with respect to V1. That's why this is 1 and this is 0. So this term here is, dV1, dV1. This is dV2, dV1. So by setting that equal to a 1 and 0, we said we want the derivatives with respect to V1. So by the time we get through with this, we have derivatives only with respect to V1. If we have additional inputs, like we do in this case, we have to run this right-hand side again. We have to run it nx times, right? So just like finite differencing and complex step, the complexity is going to scale with the number of inputs. Okay, so that's a bit of a recap. Let's go back and talk about this problem. Remember, we saw this problem and we used it in the context of showing why symbolic differentiation can be really problematic. So we can do AD, the AD we've been talking about on this very easily, right? This just involves adding numbers, the sign of a number. And there's not really much that we need to overload here, and we can then do AD very easily. And that's not going to explode like we saw, right? Because just like this loop, every time we're just evaluating the sign, same thing with the derivatives. We're just going to be doing that, cosine and then the chain rule thing. So it's going to be a very small number of operations. And again, we're just storing numbers at each sequence, just like we do here for the function value. So this is what we call operator overloading, what we've been doing, right? And that's where we did something like the sign of this dual number. We redefined it to return the sign of the value that was in there, and then also the derivative side. So this would be like the cosine, and then we multiply by the chain rule, which is like the derivative that number was holding. Okay, so that's what we did before. This is called operator overloading. But there's another way to do this that we haven't talked about, and it's called source code transformation. Okay, and the idea of source code transformation is that we take the code that we wrote and we send it over to this parser. And the parser is then going to give us back a new code that is going to compute the function and the derivatives together in one code. So in this case, it would look something like this. It would be f equals x, and you probably can't write f dot in your code, but this is just going to save space here. Just, you can call it whatever variable you want. For I equals 1 to 10. And then we have the same thing, f equals sine of x plus f. And then it adds this new line, f dot equals x dot plus f dot times the cosine of x plus f. And then that's the end. And then at the end of the loop, it returns f and f dot. So I didn't write this code. Well, I guess I did write it. You wouldn't write this code, literally, right? What happens is you write this code, you give it to this AD source code transformation tool, and it spits this out. So this is something that is generated. Notice that, it's got the same things. Of course, we don't want it to actually change how the function evaluates, but it added additional lines of code so that the derivative can be computed along the way. So these are two different approaches to doing this. Operator overloading tends to produce I guess a cleaner way to do it, in the sense that my original code generally doesn't have to be changed at all, right? Like it stays as is. I import a package that is an AD library that's overloaded all the functions that I need, and I just run it. The original code is unchanged, and I get back functions and derivatives. Source code transformation, on the other hand, I take a code, give it to this transformation tool, and I get a new code. So why would we do one versus the other? Well, like I said, operator overloading, the nice thing about it is that you just work with one set of code, and you don't really have to do, you don't have to really change it. Sometimes we have to make minor changes to make something AD compatible, but usually these are fairly minor. So that's nice. Source code transformation, on the other hand, we're working with kind of two codes here, and inevitably we want to improve our analysis, so we go back and change code. So we have to go back and change it here and rerun the tool to get this. So sometimes that can be a bit tedious. We usually set up some automated tools to make that easier. But the advantage is, and this really is going to depend on the language, how strong of an advantage this is, that this has the potential to be faster, right? Because I can compile this, especially if it's an interpreted language. This is going to be faster, whereas in things like MATLAB and Python that are purely interpolated here, or these interpolated languages, it's going to have to look up what the overloading each time, and that just is slower. In Julia, on the other hand, this is very fast by the design of the language, and so there's not really so much a penalty to operator overloading, but this will really vary by language. It's nice to have these options because sometimes one is preferable depending on, again, the language and the type of analysis you're doing. Okay, let me do a little demo here. I'm going to switch what I'm sharing over to MATLAB real quick. Okay, so I'm going to show you three ways. Let me scroll down here first. So here's this function that we've been looking at, this kind of simple function that's got a loop. and we put in a big number. I mean, actually, this is really not a big number, but bigger than we've been looking at. And so here's a function that we want to take the derivative of. And the first way we're going to do it is with symbolic differentiation. So, you know, you don't really have to know the syntax, just kind of follow along what the idea here. We define symbols, and MATLAB can do a symbolic derivative. And I can't actually print this. We showed how this keeps getting bigger and bigger. For 300, it will quit. I mean, MATLAB will just give me an error, so this can't be done. But as long as I don't print it, it actually is fine. It can store that in memory, and I'm going to evaluate it at x equals 0.1. Okay, so that's the first method. The next, I'm going to do this operator overloading, and this is a package I just downloaded on the MATLAB Exchange. So this is not my own. So it's doing operator overloading. So notice I'm calling function here. I didn't have to change anything in the function. I just changed how I initialize the variable I pass in. So this is now a dual number. This is the x value, and this is 1, the dual part. So normally x, right, is a vector here, and this would be a vector usually of all zeros except for a 1 in the element of x that I want to take the derivative with respect to. So if I want derivatives with respect to x3, then I'm going to get 0, 0, 1, and then a bunch of zeros, right? And I have to then repeat that if I want the derivatives with respect to each x value. And so then this gives me a derivative. And by the way, all these methods are going to give me the same exact derivatives to machine precision. The last approach is the source code transformation. So I'm calling this function that I defined here, which notice it's what we looked at. Well, it's a version of what we looked at. It's something that, you know, I gave a parser, I sent this code to it, and it spit out this. And I don't think MATLAB has the ability to do that. Maybe, I'm sure there's some tool. I actually did this in Fortran, using a Fortran tool, and then just rewrote it here in MATLAB. But this is the idea. So I'm going to run all of these. And like I said, they're all giving the exact number. I'm really more interested in looking at the time here. So it's running. A few seconds. All right, so notice symbolic differentiation is quite slow. Took almost 8 seconds here. It took about a second for the overloading one, and then the source code transformation was very, very fast. Now this is really an artifact of MATLAB because MATLAB is very slow with these overloading. Like I said, again, in a language like Julia, these are going to be more comparable. There won't be such a huge discrepancy. Python, there's going to be a big difference too, but in Python, we usually call a lower level language, at least we do, like Fortran or C, and do the AD there, so that the speeds are going to be still fast with either approach. But this is just something to keep in mind, that this is always, I mean, not always, but this is generally intractable. This generally has the potential to be faster. Whether that's significant or not, like I said, really depends on your problem in the language, but certainly in MATLAB, it's hard to make overloading be fast. Okay, let me switch back to our screen here. Okay, there we go. All right, so a really cool thing though is that unlike finite differencing and complex step, oops, sorry. Algorithmic differentiation has the potential for a totally different approach called reverse mode. So with finite differencing and complex step and the AD we've been talking about, which is forward mode, we saw that it scales with a number of inputs. I have to recall the sequence of calculations in my function basically for each input. Reverse mode is the opposite. It's going to scale with the number of outputs. I'm going to have to call my function for each output. This is a unique advantage that finite differencing and complex step doesn't offer, and can be really a game changer in cases where, let's say, I have many inputs but few outputs. So if I have many inputs doing finite differencing or complex step, that's going to take a lot of function calls and forward AD. But if I use reverse AD and I only have few outputs, I only have to recall that function a few times and still get all the same derivatives. So this is a really powerful tool in our toolbox. We're going to do a little bit of the math, and then we'll do some examples. So let's first go back to what we were discussing with the chain rule. Remember, the idea is that a given operation, VI, is going to depend on so we'll write as a function, is going to depend on, in general, only things that occurred before it, right? So again, like we said, we can unroll the loops and everything. So it only depends on things I-1 and backwards. In general, if we think, well, in lines of code, it may be more things, but if we think about an operation, it's almost always just one or two things, right? It's not this big long list, right? It's like the cosine of something or multiplying two numbers, right? But it could be, more things. So we'll just write here in this general case. All right, so recall that when we did the forward case, what we're interested in, let me write here, let's say forward, what we already did. In both cases, what we're interested in is these derivatives. So I want the derivative of VI, say VI is an output potentially, or it's just an intermediate calculation with respect to some earlier variable, VJ. And so we could say, well, that's going to be the partial of VI with respect to some other variable that line depends on, times the derivative of that variable with respect to VJ. And we have to sum over all the k's because VI could depend on many k's. Potentially have to sum over everything from J all the way up to I-1. But as we said, typically, right, it only depends on one or two things. So K is, the number of terms in that sum is usually just like one or two things. So what we've done here is we've fixed I, right? We've fixed I. We're taking the derivative, backwards. We fixed J, this denominator. We're taking the derivative with respect to one input, and we are incrementing over all i's. Okay, so we're incrementing over all these outputs. So we fix the input, and now we're marching forward and seeing how that variable affects each of my outputs. Okay, well, now let's look at reverse. Okay, reverse mode is going to be the opposite, and still, well, sort of the opposite. We're still interested in these same derivatives, right? And what we're going to do is maybe it's a bit unintuitive. It's going to take a little bit to write this out for yourself to kind of think through it. But we're going to do this. Okay, so still going to use the same chain rule. Actually, I'm going to write the denominator first. I'm going to now think about how the variables in here depend on VJ, the variables in this operation, VK, depend on VJ, and I multiply by the total derivative of my output of interest with respect to those variables VK. And I still need to sum over K, that's the repeated variable here. I'm going to sum potentially all the way up to J plus 1 over I, but though again, it's usually just going to be a few things. This list may be longer than one or two, as we'll see. So what we do here is we fixed I. We're going to fix the output that we want to take derivatives with respect to, and we're going to work backwards. We're going to decrement J. Okay, so we're going to start backwards with one output and work our way back to all of the inputs. So notice this here. This is maybe, it's perfectly valid math, but it's not the way we usually do this. But if you think about, these terms canceling, right? They don't really cancel, but again, it's just kind of a check here to make sure we're consistent. And then we've got an I left on top and a J on bottom. That seems to check out. All right, so let's do the example we did before, right? We had an example where we said, let's say there's 4 variables in my program. And at the end of the day, this is the input I care about. This is the output I care about. So I want df dx. So before we worked forward, so with reverse mode, we're going to work backwards. And we're going to do it by fixing I. We're going to fix this numerator here. So we're going to take the derivatives of, we're going to start backwards at the end, right? Of V4 with respect to V4. And that's just 1. That's easy, right? So we're going to keep working backwards. And like I said, we're fixing the numerator. So now I'm going to take the derivative of V4 with respect to V3. This is different than what we did before. Before we kept the denominator part was the part that was fixed. So we were always taking the derivative with respect to the same X. Now we're taking the derivative of the same output, and then we're changing the input. So we're going to work back, and eventually we'll get to dV4 dV1 which is what we want, right? df dx. Okay, so dv4, dv3, it helps me to, I always hesitate doing this because it's kind of backwards thing. It helps me to think about the denominator. That's the one that's going to stay the same. So now I have to think, okay, so what things could depend on v3? It's only 4, right? That's the only other variable. And then by the chain rule, I'm going to be left with dv4, dv4. Okay, so that's not super interesting. Let's do the next one. dv4, that one stays the same, right? It's the denominator with respect to v2. And now v2 is the thing that's going to stay here. And I'm going to take the derivative of everything that could depend on v2 later. And that's going to be, say, v4. And then there's going to be the other one, v3. And then by the chain rule, this is going to be dv4, dv4, same as above. And this one is going to be dv4, dv3, for example. Okay, and you can check by using that cancellation trick and looking at the numerator and denominator, this makes sense. But what's going to happen, just like before, is that as I compute these total derivatives, that dv4, dv4, I'm going to reuse them. And this one is going to be reused, right? I'm always using things that I already calculated. So every time I'm only looking at derivatives with respect to a single variable, partial derivatives. In this case, how things are changing with respect to this v2. There's one more line I need to do, dv4 with respect to dv1. I'll have you try that on your own and then go look at the book and see how you did it. It helps to kind of write this out because, again, this is even less intuitive than the forward mode. Okay, so we're going to do a few more examples, but here I want to just look at it another way. You can think about it, this graph here, right? In this graph, what happens is that we're drawing as we go from inputs to outputs. And in forward mode, we start with one input and work our way towards all the outputs, and we get the derivative with respect to every output. In reverse mode, we start with one output and work our way towards all the inputs, and we get the derivative of one output with respect to all inputs. So here's a key difference in reverse mode that makes it a bit more complicated, is that with forward mode, as I work from forward to these outputs, that's exactly the same sequence of operations that I do anyway to evaluate my function. But in reverse mode, as I'm working back to see, well, what does F1 depend on? I don't actually know that beforehand. So I have to actually create this graph. I have to run through my code forwards, create this graph, and then I go backwards computing derivatives until I work my way through the inputs. We'll see this again in a second, but just keep that in mind. So, oops, I already wrote this out. Let's do an example. I'll rewrite this again. Okay, we're going to do this example. This is the example that we did already, the simple one with 2 inputs and 2 outputs I was showing at the beginning of today. So let me just write out real quick what that looked like on the left-hand side. This is just the standard function evaluation, no derivatives here, right? So we multiplied 2 things together. We took the sign of something, and then we added 2 things, and we squared something, and then finally we got the other output by adding in a couple of things. Okay, so let's do the reverse mode. And remember, I have to pick one output. So here I am going to pick output 7. That's the one I'm going to do with respect to. So I'm going to take dv7 with respect to something. That's the thing that's going to change. So I'm going to change that each time. So I'm going to start again at the back. dv7 equals 1. And then I go down dv7. Remember, it's now the numerator I'm changing. Whoops, no. I just did it like forward. Right, so again, it's easy to get these mixed up, even though I just said it. dv7, dv6. Okay, that's right. All right, so in that case, I'm going to look at things that depend on v6, and the only thing that could depend on v6 is v7, right? Because that's the only variable that comes later in this case. And then by the chain rule, dv7, dv7. And in this case, if I look at what's the partial of v7 with respect to v6, that's just 1, right? So then this is just going to give me dv7 over dv7, which is just a number, in this case 1. So that's pretty straightforward. Let's do the other one. Next one, dv7, dv5. All right, so if I was to write this out in general, I'm going to write it out, but then I'll show you how we wouldn't normally do all this. I have to think about the denominator here in reverse mode, and I'm going to think about all the things that it depends on potentially, and that's v7. And then v5 or 6 helps me to do it this way. And then do the chain rule. This is going to be 7 over 7, and this is going to be 7 over 6. Okay, again, this takes some practice, and even I keep mixing this up. So write it out on your own to try and then check. But let's look at this. Okay, so again, these total derivatives are things we already have. These are the things we now are going to compute for this new operation, just looking them up based on our derivatives that we know. So the partial of v7 with respect to v5, well, v7 doesn't depend on v5, so that's 0. The partial of v6 with respect to v5, v6 doesn't depend on v5, so that's 0. Right? So that's it, right? And again, these are partial derivatives, so we're not going backwards. We're just looking at that one operation. So here's why, there's an example of why we need that computational graph. Generally, we would not write all these out and then plug in zeros, right? The computers, we don't have to do that. What we're going to do is we're going to say, okay, look, the partial of v7 with respect to v5. To do this in reverse mode, I need to know everything downstream of v5. What are the things that depend on v5, right? Because those are all the things that are going to show up here. So when I have my computational graph, or let me say it this way, if I don't have a computational graph, and I'm just moving along, right, in my calculations, I have no idea who's going to use V5, right? Like I just calculated V5, and there's more stuff coming down the road. I don't know if anybody else is going to use V5. Who's going to use it? I don't know until I evaluate it. But once I have that sequence and I have my graph, I can see, oh, there's no nodes, right? Like if this was the end, and well, this is kind of too simple to say, but like, let's say this was V5, and I was looking after that, there's nothing after that. Nothing uses V5. So I would know off right away that this is 0. That helps me know what terms I need to include in here. And this is why I need that graph, because as I'm going forward, I actually don't know those dependencies. So I first create that graph going forward, and now I can go backwards using the information from that graph and fill in these derivatives. So let's just do one more. Let's show you that, dv7, dv4. So here, I'm taking all the things that depend on v4. And from my graph, or just looking at this, I can see that the only one is v5. So the only term that's going to appear here is the partial of v5, and then by the chain rule, that's going to be dv7, dv5. So again, this is going to be a term that I already have. They're always, because we're doing this reverse, they're always going to depend on things I already have. And here I've got to use my chain rule. dv5, dv4 is a simple thing. It's just, this is just, you know, I'm looking up for my differentiation rules. That's just going to be 1, and so I'm done. Okay, so I encourage you to you know, work through that on your own, finish up the last of those, and see if it makes sense. Okay, whoops, sorry, I went through this already once, and then it didn't work somehow on the recording, so I had to redo this. But here's a contrast between forward and reverse for that simple example. Notice in forward mode what happens. In forward mode, what I'm doing is I picked one input. In this case, I'm taking the derivative of some variable with respect to v1, and I'm marching that forward. What's the derivative of v1 with respect to v1? Now the derivative of v2 with respect to v1, derivative of v3 with respect to v1, and I march forward. So when I get to the end, I have the derivative of my outputs with respect to v1, just one variable. But notice that adding more outputs is generally very little cost, right? As I add another output, you know, it doesn't add much for me to also get those derivatives. Just like if I have this long engineering calculation and I want to add another output, it's usually going to depend on a bunch of inputs I already have. So it doesn't add much cost to add another output. Similarly, adding another output derivative is very little cost. But if I have more inputs, now I have to run that whole sequence for each one of them separately. That's going to cost, right? So again, in terms of that computational graph, forward mode is going to be desirable if I have, say, a few inputs here's my inputs, here's this graph, right? And I've got lots of outputs. So imagine I've got this graph. These are all the intermediate nodes, and I'm just drawing a jumble here because I don't really want to draw it. When I do forward mode, I do one input at a time, and I get all of these outputs at once. And then I do another input at a time, and I get all of these outputs at once. So forward mode is going to be advantageous in that situation. Reverse mode, on the other hand, notice I'm taking the derivative with respect to one output, in this case, V7, and then I'm just changing, I'm working backwards on that variable. So this is derivative V7 with respect to V7, derivative V7 with respect to V6, derivative V7 with respect to V5. So as I work back, getting the derivative with respect to additional inputs cost me very little, just usually another line or whatever. But if I have more outputs, I have to do an entirely new sequence. So again, the advantage here is going to be situations where I have lots of outputs and a few inputs, right? And I've got a big whatever graph here, because I can work from one output, I can work backwards and get the derivative with respect to all inputs at once. And then I do the same thing for each output, right? So it's going to scale with the number of outputs. This is a design choice that I didn't have with the other methods and can be a real game changer. And in fact, there are times where we're intentionally going to take advantage of this. Often, the only way to reduce inputs in an optimization context, right, means just I have less design variables, and that's less desirable if I want more. But on this side, these are our objective and constraints. I can actually keep all the constraints that I want, and there are ways to aggregate constraints or combine them. Crudely speaking, you could say we could take a bunch of constraints that are somewhat similar in context and take the maximum of them. Really, we do like a smooth max. There are these constraint aggregations, so we could reduce the number of outputs. That would allow us to have, maybe take advantage of some real efficiencies using these reverse mode things. This is something we'll also talk about a bit more next time in a different context. Okay, sorry again. This is me redoing this. So another way you could look at this, the same idea, is in terms of the Jacobian. So the Jacobian, this is the Jacobian that I'm interested in, right? Like I want df/dx at the end of the day. Let's say it looks something like this, and these are all my x's, x1, x2, my inputs, right? And then these are my outputs, f1, f2. And when I do forward mode, each time I do forward mode, I'm doing it with respect to 1x, right? So every time I do forward mode, I get an entire column of my Jacobian. And then I have to do it again, and I get another column. So I have to do it each time. Whereas in reverse mode, right? What happens in reverse mode, I do with respect to one output. So I get an entire row of my Jacobian each time. So you could look at it in terms of the Jacobian too. If I have a Jacobian like this that's wide and short, reverse mode would be an advantage potentially. Whereas if I've got a Jacobian that's tall, right, and skinny this way, then forward mode might be an advantage. Now that's not necessarily strictly true. It's really maybe helpful on the extreme ends when we have way more inputs and outputs or way more outputs and inputs. When they're more comparable, it's harder to say, or where they're more similar, because in part, as we talked about the reverse mode, what happens is we have to create this computational graph. So I actually have to go through that forward pass, and that means there's a memory overhead. I got to store a bunch of stuff in memory. So that has a higher computational cost. There's a bit more complexity with it. So when they're more comparable, often forward mode will still win, even though you might not strictly determine that just based on looking at the number of inputs versus outputs. But as we get a little more imbalanced, reverse mode, that memory thing will start paying for itself at some point. Okay, one last thing here, and this is so let me start here. This is that same sort of iterative code we looked at, right? And we looked at this already. This was source code transformation in forward mode. Well, we can also do source code transformation in reverse mode. That's what this is. Okay, so again, this is where I take my code, give it to some other tool, and it spits back a new code that says, hey, here's the code that will compute your function and your derivative. And I added some lines of code for you. And here it's doing it in reverse mode. So you can see that this first part looks the same, more or less, as here. Well, actually, somehow I changed the example I did is different. So this should be 20 to be consistent with the others. Anyway, um, so what's happening here? This is all the same. It's doing. You can see there's these push and pops, and this is basically creating that computational graph. So this is what we call a stack in computer science. So you could think of it as push. It's putting it's saving these numbers, it's saving these function values in this array here, right? And pop means it's just going to take the last one in and pop that out. So it's doing it in reverse. So push just says, let's save all these things because I'm going to need them in this computational graph. And now here's the reverse mode. I'm going backwards and I'm taking the last thing off the stack there and working my way backwards. That's just what that does. It's just a structure where we put things in and then pull them out in reverse order. Okay, so there's really these four flavors of algorithmic differentiation for the combinations of either forward mode, reverse mode, and doing operator overloading or source code transformation. And I know some of the math and things we did can be a bit fuzzy. And like I said, I encourage you to work through that and think about it. But I wouldn't be too worried if you didn't capture all of that. But the main things that you really should take away is try to understand the advantages of when you might use forward mode versus reverse mode, and understand these pros and cons of source code transformation versus operator overload. So we have these kind of four possibilities, and that is really useful to have those. And this has been this is an extremely useful tool in optimization and in other applications where you want derivatives. It provides some really unique advantages. Okay, so that's going to be it for algorithmic differentiation, but not the end for derivatives. We're going to talk about more things. You might think there's nothing more to say about derivatives, but there is. And so we'll see you next time.